Unit 4, homework, FRQ, question number 3. So in this particular case, we're back to an old standard, especially in part A. We're given a chart, and anytime you see a chart like this, most often, now when we get into Riemann sum and integration, we have some more. Anytime you see a chart, you'll always look to have this. But question part A is guaranteed. If it's a chart question on the FRQ, you will be asked this question. It's very, very rarely do they not ask this when you have a chart like that. So it says use the data in the table that describes the cooling soup. Of note, it tells you it's twice differentiable in the function up there. So use the data in the table to approximate h prime of 5. So that means all we can do is then use the average rate surrounding the 5. So I'm going to have to use these two coordinates. And don't forget, it's an approximation, so use the approximation symbol. So I picked h of 8 and h of 3 to help me do that, and it's just the slope formula. And it says here, show the computation that led to that answer and use correct units, explain the meaning. That's when you have to write it in sentence form. When t is equal to 5 minutes, the soup is cooling, you have to add the soup. You can't just say that the rate is this. The soup is cooling at a rate of, and I'm using the word cooling, that implies negative, so don't make it a negative. Even though the value is negative, don't make it negative. The rate is cooling at a rate of 13/5, or you could rate it as a decimal if you wanted. I guess that would be 2.6 degrees Celsius per minute. So don't forget to include the units. You need to include the units there. So have all of the pieces that you need. All right. In part B, there's a time t for 0 to 12 at which the temperature of the soup is 60 degrees. Now, the reason why we know this is if you look from 0 to 12, you're told that from 0 to 12, it is actually differentiable, which implies that it's continuous. So I can see that we have a value above 60. All of these three are above 60, so you can use any of those three. I just used at the end because I wanted to describe the whole interval, but you could also just use at 8 to 12, and then say the interval from 8 to 12 is included in the interval from 0 to 12, but it just adds more writing. So you need to write specifically, since it is given that h of t is twice differentiable, it implies that h of t is continuous. You need to have that it's continuous, and you know it because you're told that it's differentiable. And h of 0 is equal to 90, and h of 12 is equal to 58. I can see that 60 falls between those two values. Those are the conditions for IVT, so the intermediate value theorem. So by the intermediate value theorem, there must be at least one value for t on the interval of 0 to 12 inclusive where h of t is equal to 60. But you need to have continuity, you need to have the betweenness statement explicitly listed, and then you need to state IVT, that you're using the intermediate value theorem to conclude this. But that's review from Unit 3, really. All right, in Part C, it says the temperature of the soup is also modeled by a twice differentiable function c from 0 to 12, given the measure in Celsius degrees over time in minutes. If you know that c of 3 is equal to 80, and the derivative is, now note, this is the derivative, so be really careful here. Write the equation for the line tangent to. So for me to write the equation for the line tangent to, I need to find the slope of the line. So the slope of the line at 3 is this one, this value here. Now use your calculator. So put this in y1 in your calculator. So y1 is equal to c prime of t. Now you type that, don't write c prime of t, actually type in the function, and then you can just substitute that in. And then you're going to use the stored value, not the rounded value, in your calculator. Store this value for a so that you can use it in your calculator later. It just makes it a little bit easier. So I have to write the equation of a line using point slope form and moving the y over to the other side. That's why it's plus 80. So the slope of here c prime of 3 is equal to the slope that I need for, and you're told that 3 comma 80 is a point on the at 3, so therefore I have all the pieces to write the equation of a line. So here's my slope, that was my slope, and then x minus the x coordinate, and then plus the y coordinate, which I moved over from the other side. And don't forget, you're estimating c at 5, so that's an approximation symbol. So we're going to take and substitute them, because I don't know what the function actually is, so I'm going to use the linear function or the linear approximation to help me do that by substituting in 5 into that function. So in our case, we get that it's, and you can just put that in the calculator, right? You've already stored this in there as a, so a times 5 minus 3 or times 2 plus 80 should have given you a 73.803. Don't forget at least 3 decimal places, so you could do more, but never less, unless it terminates. So part D, based on the model given in C, at what rate in Celsius per minute means that you're taking the rate of the rate. Is the rate of change of the temperature of the soup changing? So we're asking how fast is the change changing? So that means take the second derivative. I wrote out what the second derivative is, substituted in the 3 because we're asking at 3. Using your calculator again, you can use your calculator for this. Make sure you write down what the second derivative is equal to. And then the rate of change, the temperature is changing, the temperature of the soup, I forgot. Temperature of the soup is changing is 0.155 degrees Celsius per minute, or you could write it with the units like that. When t is equal to, when t is equal to 3, I guess that got erased. When t is equal to 3. And that's the last question.